Okay, good afternoon. Let us begin our journey of statistical inference. Okay, so basically there are two major parts of statistical inference. One is for estimation, the other one is hypothesis testing. So we will discuss hypothesis testing in the next chapter. By the way, I think there's an announcement in the Luminous for ST2334 saying something like the lecture ends this week, this Friday or something like that, but it does not apply to us. Yeah, unfortunately, you're in the wrong group. All right, I think that announcement is targeted at group 2 students. So for us, sorry to, we still need a few more meetings, all right, up to maybe week 13. That's also good, huh? So that means at least you have time more. I mean, you have more time with the lecturer. All right. Okay. So for estimation, so we begin with. Okay, the idea is that we want to know something about the population. We try to estimate something about the population, and we base the information about a sample. So a sample, we represent it by x1, x2, up to xn. So that is a random sample. And they're supposed to be independent and identically distributed. So we begin with talking about statistics. All right. Statistics. All right. This word statistics in statistical inference context, it simply means that it's a function of the random variables, okay, or random sample. So basically, anything that you can express as a function of, okay, so a sample, a random sample means x1 up to xn. We have n random variables taken from the population, and any function of x1 up to xn is considered as a statistics. Of course, statistics also means that a collection of numbers or information about a system. It's also called, those information collected are also called statistics. Like what is the, in a ball games, so especially in America, or in basketball, so how many, what do they call it? Okay, I'm not familiar with basketball, but how about football? So you can count how many penalties or how many goals are. Goals is obvious, all right. But then statistic means that how good the team is. So usually it depends on, for example, how many time or the time that you keep the ball, the team keep the ball. So if the time you keep more than 50%, that means you have a control over the whole game. Like if you control 90% of the time, the ball, then that means your team is much stronger than the other team. All right, so this kind is also called statistics. But in statistics context, statistics means that it is a function of the random variable. So an example is x bar. So x bar is the average of x1 up to xn. So that's an example. All right, another example, this function is much harder. Okay, what is a function? So basically the idea is that, okay, I got any x1 up to xn, and then through this function, I map it to one point. That is my function, all right? So an example is that, okay, I take the average, so that's one function. I can also just take the maximum of all this x1 up to xn. So that's another function. So median is also a function. So among all this, I take the middle rank. So that is also a function. Then this is also a function. I just take it as x1. That means this function that I'm looking at is just the first random variable. So that is also a function. So that is considered as a statistic as well. All right? Okay. So this one is a function of x1 up to xn. All right? at the same time, it also involved, okay, mu and n. So basically this means that it's x1 minus mu square plus up to xn minus mu square. And then we take the average, sum them up and divide by n. So this is the function. Now, for statistics, not just a function of the random variable, you also need to make sure that once you got the data, you are able to compute the value of these statistics. So if we take a sample, what we get will be x1 up to xn. But we don't have the value of mu. So in other words, even if you got the sample, you are not able to compute the value of this quantity. So in that case, this is not considered as a statistics. So in other words, the statistics, all right, is a function of the random variable for which you can calculate the value once you take the sample. That means there are no unknown quantities in the expression or in the function. In this case, this is not a statistic because mu is not known. But if mu is known, then this is considered as a statistics. Right? If mu is known, then it's a statistics. Is this a statistics? Yes, this is a statistics because this is a function of x1 up to xn, the random sample. At the same time, we can calculate the value of these statistics once we take the sample. Everything is known. Once you have the sample, you have the realization of the random sample. All right, so it's known. Mu known, then it's a statistics. All right, so now, suppose we are interested in the population parameter, which is mu, the population mean. So we can have statistics, all right, to obtain upon estimate. So that one is called an estimator. So it's a bit confusing about these two words or two terms. All right, you may not differentiate these two, but in statistics, we try to make it separate. So estimator is a function of the random variables. In fact, it's a statistics. That means it's a random variable. First of all, it's a random variable, and it's a function of the x1 up to xn. All right. So it basically is just a function. All right. So an example is x bar. Another example is s squared. So these are example of estimator. Of course, estimator has to estimate something. So in fact, this is usually used to estimate mu, and this is estimate sigma squared. All right, mu and sigma squared are something related to the population, and x bar and s sample variance are something to do with the sample. So this is just a formula for you to estimate a function for the random sample that to use to estimate the parameters. All right. Well, estimates are sort of realizations of the estimator. Or let's put it this way. It is when you take the sample and you really look at the value of each sample. So like I say, I toss a coin. The outcome is either head or tail. So I define a random variable 0 or 1. All right, 1 is a head and 0 is tail. Okay, if I do not toss the coin, I don't know what is the value of the random variable. I don't know it takes either 1 or 0, depends on the outcome whether it's head or tail, with probability half. But once I toss it, though I know that the outcome is the head, for example, then I got a realization of that random variable. So the same apply here. Once you take a sample and you really look at the sample values, that means what is x1, what's the value of x1, what's the value of x2, all right, and so on, then that one is called estimate. So estimate usually refer to a number which obtained by looking at the sample value. You know, you watch, you get the value of the sample. But in general, I just say that, okay, I take a sample. So the sample is represented by capital X1 up to Xn. So the estimator is a function of this capital X1 up to Xn. So like the X bar and S. So for estimate, we'll use the lowercase, which means that this is really a number. And how do we get this number? Is after we take the sample and look at the sample and get those numbers from the sample. All right? If you just say, I'm going to toss a coin, so the outcome is head or tail. So I did not toss the coin, I did not know the outcome. So the estimator will be a function of the random sample. All right? Okay, so X bar is an estimator of mu, and the value of X bar, this value, when I say value, we already realized the random variable. All right? So we look at the sample and then get the values and compute this X bar, that means the average, and that one we denote by X bar. That is an estimate of mu. All right? So that one is called a point estimate because it gives you an estimate which is just one value. So a point estimate. Later on, we'll discuss about something called interval estimate or interval estimator. All right? So if a sample mean of a random sample taken from a population with mean mu, this one 5, referring to the sample mean, it does not refer to mu. We don't know the mu. So this particular sample gives us the mean equal to 5. All right? So the point estimate now of mu is 5. So in other words, we estimate mu by X bar, the sample mean. This is a random variable. But once you draw a sample and we calculate X bar equal to 5, that means from this particular sample, the average is 5. Then we use this as an estimate for mu. All right? So there are two things. One is a way that you want to estimate mu. So that one is estimated, a function of the random variable. The other one is you take a sample, you look at the value, and then calculate the values of this estimator. That one we call it estimate. But maybe if you are not so sure, but just make sure that you know that one is a formula for you to tell something about the unknown parameter. That is estimator. But once you take the sample, you have the values. You measure everyone in the sample. Then you can calculate a number, a value for this random variable. That is called estimate. All right? So different random samples give you different point estimate. All right? So in other words, this is an estimator. We can have many estimators. I can use X bar as an estimator. I can use this X1 as the estimator. I can use the median as the estimator for the population mean. All right? So we have many. But then for each estimator, when you take different samples, then you have different values. All right? So that's what I mean here. So you have to distinguish. For an estimator, when you calculate the estimate, it's based on a sample. You can draw many samples, therefore you have many estimates based on the same estimator. All right? But on the other hand, you also have many estimators to estimate the parameters, the unknown parameter, in this case, mu. In fact, a question natural that you will ask is that, if I have so many, which one should I use? Which one should I use? So I think X bar seems to be a very popular. There must be reason behind why X bar is used to estimate the population mean. All right. One of the properties that the X bar has is that it is unbiased. So we will discuss why it's unbiased. All right. Interval estimation. So interval estimation obviously is an interval. So have two numbers instead. So we try to get an interval so that we try to estimate these unknown parameters. All right? So an interval consists of two statistics. All right? That means two functions of the random variable. A very simple example is like this. X bar minus 10, x bar plus 10. All right? So this is an example of interval estimator. All right? So this is a random variable. X bar is a random variable. You minus 10, it is a random variable again. And this is another random variable. And we are pretty sure that this x bar minus 10 is less than x bar plus 10. All right? So, so this satisfies this. All right? The statistic for the lower limit and the statistic for the upper limit, the relationship is that the lower limit must be less than the upper limit. So this constitutes an interval, and we can determine the probability of theta between this random variable. Okay, I try to use this is capital letter of theta. This is the capital letter of theta. So theta, I put a hat there, means that this is an estimator. All right, and it estimates, I use L to denote that it is for the lower limit of this confidence interval, and U to consider upper limit. So this statement simply means that we try to find out the random variable, all right, random interval that cover theta with probability maybe 1 minus alpha, for example. So that's what we are going to do. All the formula that you come across when you talk about confidence interval, you must come across this one. Like, for example, x bar plus or minus z alpha for 2 sigma over root n. So this is a confidence interval, a formula for confidence interval under certain conditions. All right. So this one is one of the examples of confidence interval. So this one, the probability of this cover the true mean with probability 1 minus alpha. So that's what I said here. All right. So here is an example. If sigma square is known, then this is the lower limit of my interval estimator. This is the upper limit. All right. So then this is an interval estimator. This is a random variable. This is another random variable. And this random variable is less than this random variable. Why is it lesser? Is it obvious? If this is your x bar, if this is x bar minus 2 sigma square will be here. Right? Because this is positive. So minus a positive number must be smaller. So adding a positive number must be bigger. So this number must be, this quantity must be bigger than this quantity. All right? Okay. So this is an interval estimate for mu. In fact, the interval estimate for mu usually is in this form. X bar, because x bar is used to estimate mu. So the confidence interval will be something like this. X bar plus or minus, okay, between x bar minus some constant times the standard error of x bar minus the same constant times the standard error of. So all the intervals that we discussed basically are in this form. In this form. So it's x bar, which is used to estimate mu. So I subtract from x bar certain quantity. This quantity basically is how many standard deviation, standard error of x bar. So we subtract certain standard deviation of x bar and add certain standard deviation from of x bar from the x bar. All right. So in other words, so this is my x bar. So the confidence, the interval will be this one. I minus x bar minus standard certain constant times the standard error of x bar. So in particular, if sigma is known, this is something like this. K standard error of x bar is sigma over root n. So the upper side will be x bar plus k times sigma over root n. And what is k? So k will determine how the probability of covering the true parameter. All right? Let's sidetrack a bit to talk about properties of estimator that we want. So unbiased estimator is what we want. Okay? So an estimator is unbiased estimator for parameter theta if expectation of it equal to that parameter that you want to estimate. All right? So an example is x bar. We can show that expectation of x bar equal to mu. This holds for any distributions. All right? It's a good exercise to show that expectation of x bar equal to mu. In other words, if x1 up to xn taken from a population with expectation of x equal to mu. So that means any x here have expectation equal to mu. You just take n of them. So x1, x2 up to xn. So each of these will have expectation same as the population mean mu. Then now you have to work out what is the expectation of a function of all these x1 up to xn. And it turns out to be mu. So x bar is the unbiased estimator for mu. So the same question. How about x1? Is it unbiased? Is it unbiased estimator for mu? So the answer is yes. Why? Because expectation of x1 is just like anyone in the population, so it's equal to mu. So it's unbiased. All right? How about how about x1 plus x2 over 2? Is it unbiased? Yes, it's unbiased. How about this one? x1 plus 2x2 divided by 3. Is it unbiased? Yes, it is also unbiased. All right? But not this one. x1 plus x2 divided by 3. This is not an unbiased. Because the expectation of this one does not equal to mu. It's equal to 2/3 of mu. So that's not equal to mu. All right? We can also show that this sample variance, expectation of sample variance, is equal to sigma squared. So I won't go into details, but I think you may use this formula to prove it is unbiased. This may be easier to work with. All right? This is the computational formula for S squared. And on top, expectation of xi squared minus the square of expectation is equal to our variance. All right? This is a useful formula to show that it is unbiased. We need to know to compute this one. Do we know this one? Yes. This is sigma squared. Do we know this one? Yes. It is mu squared. So the expectation of xi squared is basically equal to mu squared plus sigma squared. So we can show that expectation of this quantity is equal to sigma squared. So because of that, so this quantity, this is an example, show that we have a bias estimator. So in other words, I can show that expectation of t defined here, in fact, is equal to this one. Is n minus 1 over n sigma squared, which does not equal to sigma squared. So it's a bias estimator. All right? So bias. But this estimator, although it's biased, which means that the expectation of t does not equal to sigma squared. But think of it, if n getting bigger and bigger, so what can you say about n minus 1 over n? It's getting close to 1. So in other words, although expectation of t does not equal to sigma squared, but then it goes to sigma squared as n goes to infinity. All right? So that means if n getting bigger and bigger, then this t is getting very close, the expectation of t is very close to sigma squared. All right? So we call t a consistent estimator. That means if your sample size is big enough, the expectation of this estimator is equal to whatever you want to estimate. Oh, and also the difference between your expectation of your estimator in this example is this, and sigma square. All right? The difference between your expectation of your estimator and the true parameter that you want to estimate, the difference between these two, if it is zero, then that means your estimator is unbiased. So the difference is non-zero, then that represent a bias. We call that a bias. All right? Bias. All right? So you can see that the difference in this example 3, this is n minus 1 n sigma square minus sigma square. So the answer is minus 1 over n sigma square. Okay? It's the bias is minus sigma square over n. So what does that mean? It means that this estimated t, all on the whole, it underestimates sigma square by a bit. By how much? By 1 over n sigma square. So that means in the long run, you expect that you take many sample and calculate many t's, and they take the average of all these t's. The answer is not sigma square, but slightly less than sigma square. By how much? By 1 over n sigma square. All right? So that is the bias. And negative means that it underestimate. Positive means it always overestimate. All right? It always gives you an answer bigger than what you're supposed to be. No, not always, but as an average, it gives you an answer that's bigger than what it should be. That is overestimate. All right? All right, interval estimate, as we mentioned. So that is the random variable. So that is this interval, right? Lower limit theta L hat, upper limit theta U hat, capital theta. This is a random interval, and is the interval estimator. So once you take a sample, you can calculate the values. Then that is the confidence interval. Now this confidence interval depends on the value of your theta, your random variable, all right? And also the sampling distribution of this random variable. Okay, it depends on how this behaves, and this two basically comes from come from this theta hat. You just have to add or subtract something, all right, for the estimation of mu. All right, so here is the idea. So this is the theta hat. That means once you take a sample, you can calculate your theta hat. Then because of this formula for the interval, confidence interval, then you can compute the lower and upper limit. All right? So that is what we have. So this is the width of the confidence interval. So naturally, this width, the bigger, the better. All right? In some sense, that means you are able to cover the unknown parameter theta. All right? But then that's not very useful. Okay? When I say good, it's from the point of covering the true parameter. But on the other hand, if I give you a confidence interval, let's say, for example, I want to estimate the maximum temperature tomorrow. I say the maximum temperature in Singapore tomorrow will be between minus 100 degrees Celsius to 100 degrees Celsius. Almost correct. All right? Laughing, right? Yes. Does not have much help. But if I tell you, okay, the maximum temperature may be between 30 to 39, so I shorter the interval. In fact, this is almost true. I mean, the chance of covering the true maximum temperature tomorrow is almost 100%, except maybe something happened. So I should have a shorter interval. So that's the idea. I try to get a shorter interval. Then I said, okay, tomorrow's maximum temperature is between 32 degrees to 33 degrees. It may be off the mark. So very short interval, but then the chance of covering the true parameters, maximum temperature, may be off the mark. So we have to balance between the length or the width of the confidence interval, at the same time balance the chance that it will cover the true answer. So we have to balance between these two. All right, so for different value, we have different, different sample, we have different lower and upper limit. All right, so we want to know whether this interval covers the true parameter or not. All right, so here we try to look at the following. We want to find as random variables, two statistics, such that the probability of this random interval cover the unknown parameter theta with probability 1 minus alpha. All right. So this is the basic formula for confidence interval. But don't worry, we are only interested in two types. Something to do with mu or difference of mu's, and something to do with sigma, the sample variance, the population variance, or the ratio of the population of variance. So it's very specific. Theta may be mu or sigma square, or mu1 minus mu2, or sigma 1 square over sigma 2 square. That kind of parameters. And we want to come up with these two quantity such that the probability this random interval cover the parameter with probability 1 minus alpha. All right? So then we can calculate from a sample. We have the sample value. We can evaluate the two random variables. And we want that to be a 1 minus alpha 100% confidence interval. So this quantity, all right, once you realize it, it is called confidence coefficients. All right. So what I'm saying is like this. So this is the random variable, two random variables. So that theta in between this one with probability 1 minus alpha. I can calculate this probability, make sure that is equal to 1 minus alpha. But once you take a sample, all right, you have the numbers. You substitute in, then you have these values. Then this interval, once you take a sample, then you can calculate. Then this interval can only cover the true theta, or it does not cover the true theta. So in other words, once you realize it, then no more, like I toss a coin, once I look at the outcome, it's a head. It's no more a random variable. You have to realize your random variable. So it's no more a random variable. Then it does not make sense to talk about the probability. Okay. Once I take the answer, I see that it's a head. So how can you say that? Oh, the probability of getting a head is half. No, you have to perform the experiment and then you get the outcome. So like you take a sample and then you look at your sample values and then you calculate your X bar. So you already realize your random variable. So once you realize it, it becomes a number. So this one, the same, you once realize, then you have this interval. And this interval is either cover your unknown parameter or it does not cover. So it's no more probability. So we interpret this 1 minus alpha 100% as our confidence level. How much confidence we place on this interval. All right? So, or sometimes refer to degree of confidence. All right? So these are the lower and upper confidence limit. Now, so if the sample size n is taken, then in the long run, so many of them will cover the unknown theta, parameter theta, and so that's what we call the confidence. All right. So here is a graphic displayed. So I take one sample. I take one sample. So I have this sample mean. One sample, I got this x1 bar is the sample mean. So based on the formula of your confidence interval, I calculate the confidence interval. That is a realization. The formula, this is the formula, all right? This is the formula in terms of random variable. But once you take a sample, I can calculate what is x1, what is x2 up to xn. So I take the average of all this. I also calculate the sample, I assume sigma is no. So I just calculate the x bar. Then I substitute x bar in this formula, and I assume that sigma is known. Sample size is known, all right? Z alpha of 2 is a number from the normal distribution. So I can compute this value as well as this value. So I determine, so this is my confidence interval. This referring to this referring to this, all right? So I can compute the confidence interval from this sample. So I showed it here. Then I take another sample. So this time the sample is x2 bar. Then I use the formula again. I calculate the confidence interval. So this is the confidence interval. So I can take a third sample, fourth sample, and many samples. This is the third sample, and take many of them. Then the idea is that out of so many, about 100 times 1 minus alpha, or 95%. Let's say I fix as 95, alpha is 0.05, so I have 95% confidence interval, which means that if I take many samples, 95 of them will have will cover the true parameters. So you can see that this one have a confidence interval does not cover the true mean. This is the true mean. All right. With this true mean, the chance of getting the x bar closer to the true mean is quite high. So you can see a lot of them are quite close to the center, but a few will be off mark, quite far away, and then the confidence interval will not cover the true mean. So confidence interval attached with it is the confidence interval. So the 95% is the confidence level. All right. So this confidence level obtained from the probability of the random interval. And that random interval, in this case is like this, is for you to compute the confidence interval. Once you have the sample, you substitute in and then you get this value of this interval. Identify the interval. So there are two parts. For the random interval, it is the probability. It is this probability. The chance that this random interval upper, so this one is equal to 1 minus alpha. So that's how we interpret the confidence interval. But once you take the sample, now you calculate, and then this one is the realization. All right, this interval, all right, is either cover the true mean or not, the true parameter. But what we say is that, okay, I've followed this formula of the random interval. I take many samples, each one I calculate it. So out of so many confidence interval, I have 1 minus alpha of them will cover the true mean. So, so we are quite confident that this one that you see from this sample may be very likely, but not measured in probability, but then it's likely that it will cover the true parameters. All right? So 1 minus alpha, 100% of them will cover the true mean. Okay, so these are the basic thing. Now, more specific, we look at the parameter mu, how to construct the confidence interval. So there are quite a few formulas, but basically what you need to ask is two things. The most important thing, whether the variance is known or not. Whether it's known or not. And second one, whether the sample size is big or not. Of course, the third one is whether the underlying distribution is normal or not. These are a few things that you have to pay attention. All right? In order to pick up the right formula. Okay. So the first scenario is that when the sigma square is known, the variance is known. All right? And the population is normal. Or if it's not normal, the sample size is big. Then we can apply the same formula. And what is this formula? The formula, all right, is like this. Okay. Okay. So you have x1 up to xn, okay? And if they are normally distributed, then X bar will normally distributed with mean and sigma square over n. This we have discussed in the previous chapter. All right. Even we just have this, and we don't know whether it's normal or not. It's questionable. We don't know. But then if n is big, and when we say big, it's bigger than 30. All right. But it's not a cast on stone rule. Here we just use a reference. So whenever bigger than 30, you may consider it's big. But maybe 29 is still considered big. All right. Okay. So if it's big, then what is the distribution of X bar? It's normal with mean mu sigma square over n again. This one is only an approximation, and we can do that because of the central limit theorem. All right. So in other words, so we can put these two different cases together. One is normal distribution for the population, and the X bar is normal mu sigma square. While if you don't know the distribution of X, you can still apply the central limit theorem and get X bar normal with mean mu and variance sigma square over n, but only an approximation. All right? So we standardize it. Then here's the trick. So this is the standard normal, Z, right? So it's between these two numbers. That means it's taken from a standard normal, 0, 1. So between these two numbers, the probability falls in this region is 1 minus alpha. That's the idea. All right? So rearrange it so that this parameter mu is here. So this is my theta L. And this is my estimate, the random interval or the upper limit. Upper. All right? It's not too difficult to rearrange it. Just bear in mind, I just want mu there. So first of all, I multiply all by sigma over root n. So sigma over root n here, sigma over root n here. So I don't have the denominator. Then I move the mu to the other side and move this term back here. Oh, remember, there are two inequalities here. Basically, we're solving two sets of inequalities. The first inequality is X bar minus mu over sigma over root n greater than minus alpha over 2. That's one inequality. So you have to rearrange it so that mu is on one side of the inequality and the rest put it in the other side. All right? The other inequality is this part. So you have to rearrange it so that mu is on one side of the inequality. Mu, not minus mu, mu. So at the end, you will find that this inequality gives you this part. And this part of the inequality, this inequality gives you this part. Sorry, gives you this part. All right? Anyway, so this is my theta lower limit, and this is the upper limit. So the confidence interval is given by this and this. This is the formula for the confidence interval for mu. When the underlying distribution is normal, or if it's not normal, the sample size is big enough. But we assume that we know sigma. We know sigma. Or sigma is known. So we apply this formula. All right? Okay. So before I look at another example, I tried to sidetrack a bit. And this, in fact, is a question that always asked, or quite often asked. What is the sample size that we need? Oh, I want to do a study. How many data should I collect? All right? So it's not an easy question. So even I just interested in study the parameter mu. So I asked, how big a sample should I have in order to study something about mu? Now, by this question is difficult to answer. You must be more specific. In other words, you must state some other condition in order to address to this problem. What's wrong with sample size of 5? How do we compare with a sample size of 100? Are there any difference? Of course, there must be some difference. Otherwise, everyone would just take sample of 5. Why would we bother to take so big a sample? So there must be some other ways to measure how good how big the sample size that you need. So here is this one, x bar minus mu. Remember, x bar is a random sample or estimator that you want to estimate your mu. And because it's a random variable, you don't expect x bar equal to mu. All right? Remember, this is wrong. Why is it wrong? X bar is a random variable. All right? While mu is a constant. So a random variable shouldn't equal to a constant. What we say is that the expectation of x bar equal to mu. That is correct. Expectation of x bar equal to mu. But x bar does not equal to mu. So because x bar does not equal to mu, so therefore we can talk about the difference between x bar and mu. So here is mu. Mu fixed. Your x bar is varied. All right? So I look at the difference between x bar and mu. All right? And look at the absolute difference. All right? So we ask these questions. All right? What is the chance that this one we call size of error? How big the size of error? All right? So I'm saying that, okay, I want my size of error to be less than certain number. Let me call it E, for example. All right? I want to have a sample size such that when you calculate your x bar, the difference between x bar and the true answer should be within certain specified number. For example, I can say this is 1, for example. But here I make it general, just a number, I call it E. But remember, x bar is a random variable. So this difference or this error less than certain number, even if I say x bar minus mu less than 100 or 1,000. This is not absolutely, we don't expect that this is always true. All right, because x bar is a random variable. In fact, theoretically speaking, x bar range from minus infinity up to infinity. It behaves like a normal distribution with center at mu, with the standard deviation or standard error being sigma square root sigma over root n. All right. So what I'm trying to say, we don't expect it to be always true, or this one has to be within certain limit. So what we can say is that what's the probability of x bar minus mu less than a specified value or specified limit with a probability, let's say, equal to 1 minus alpha. All right. So this is what we can say. So now I'm saying that if I want to find out the sample size, I must specify two things. What are these two things? The first one is how much error that you want to, you can accept. That is called margin of error. That quantity, E, is the margin or the size of the error, the size of the error. All right? So we accept the difference within certain limit, E in this case. But I also have to put a probability to this statement. All right? It's not always true. No, you can never find a sample to give you that one is always true. No upper bound. But I'm only saying that, okay, the margin of error or the size of the error will be less than 1 with certain probability. Of course, I want this probability to be reasonably large. So that's why I set 1 minus alpha, or 95%, for example. All right? So basically, this one given to you, or this one given to you, this one given to you, so you have to figure out the sample size. So in this expression, there is this sample size in it, in this formula. And we try to figure out what this n is. So now I know this is correct. This is equal to 1 minus alpha. All right? So I rearrange it. So I have this one. So in other words, I know x bar minus mu, the absolute difference between x bar minus mu. By the way, I hope you know this one, right? If A lie between B and minus B, then we say that absolute of A is less than B. These two are equivalent. All right? That's how we write the things. Okay, so now we are saying that the probability of this absolute difference between x bar and mu less than this quantity with probability 1 minus alpha. All right? So now I see an n here. It's important I see an n here. So now if I specify my margin of error, let's say I want it to be within 4. All right? This difference is less or equal to 4. So what can I do? I just equate it or make sure that this is less or equal to 4. All right? Or just equate it equal. All right? Okay? So this is what we are going to do. In fact, it's better to specify that it's less than this specified error with probability greater than 1 minus alpha. All right. So I want to find a sample with size n such that the difference or the error x bar minus mu, the absolute difference between x bar and minus mu, will be less than my specified error e with a probability greater or equal to 1 minus alpha. I have so much confidence. All right? It's greater than what you specify. So in other words, based on this one, what I can say is that this, okay, I want this less than e, bigger than 1 minus alpha. So what is this e? E must be bigger than this number. Right? E must be bigger than this number because what I'm saying is that the difference within minus z alpha over 2 sigma over root n and sigma over root n. So this probability within it is this part is 1 minus alpha. So if I take even bigger interval from this one, all right, minus e to e, all right, then in that case, my probability 4 in this interval must be bigger than 1 minus alpha. All right. I want e to be bigger than this number, so that means e, from minus e to e is wider than this, this quantity. So the probability is bigger than 1 minus alpha. All right. So of course, any number greater than this number will give you a confidence, will have a bigger probability. So we try to get the smaller c, satisfy this inequality. All right? So we arrange it, n is chosen bigger or equal to this number. Any n bigger or equal to this number will satisfy the margin of error requirement. So we choose the smallest e that satisfies this inequality. That means the minimum n satisfies this inequality. Remember, n is an integer, so you have to choose the integer. But also, I just showed you how to derive the formula. So I hope you understand it, to help you to understand the mechanism behind. But I also want you to understand this sample size formula. Now, if I want the error to be small, what's the impact? I want small e. So how to achieve that? I need a bigger n. Because the denominator, e is in the denominator. So if e is small, then that means n is big. All right, so I need a bigger sample size in order to achieve to achieve the same probability with a smaller margin of error. Now, on the other hand, sigma is in the numerator. What is sigma? Sigma is the variation in the population. All right, so in other words, if your variation in the original population is large, you need a bigger sample size in order to achieve the same level of probability of the same probability. All right? So that's how we interpret it. Of course, this is another quantity. This quantity, z alpha over 2, depends on alpha. And what is alpha? Remember, our probability is 1 minus alpha. All right? What does it mean? It means that if you want a bigger confidence, bigger probability of, that means I want this to be big, all right? Then that means this number also has to be big. Because for bigger value here, your z alpha over 2 will be even further away from the mean, mu. So which means that you need a bigger sample size in order to achieve higher confidence or higher probability. So my point is, you are given a formula. how to compute the sample size. I need to specify a few things. I need to specify the confidence level, that is 1 minus alpha. I also need to specify the margin of error, the E. After that, I obtained a formula. So you know the link between N and this quantity. There are 3 quantities here. One is alpha, the other is sigma, the third one is the E. So you have to see the relationship or the impact of the change of this E, alpha, and sigma on N. So you understand the way that they are linked. So if the margin of error is smaller, you need bigger sample size. If your variance is big, you need bigger sample size. If your confidence want to increase, that means that you have a smaller alpha, a bigger 1 minus alpha, you also have to increase your N. All right? Okay. I think for the examples, the first one is quite straightforward. You are given sigma, and you are given x bar, and you are given N, and this is sigma. So you just substitute in the formula, then you can compute the confidence interval. Oh, remember, 95%. So that means alpha equal to 0.05, or alpha for 2 equal to 0.025. With all this, you are able to compute the confidence interval from this sample. So the confidence interval turned out to be 3.4 and 3.6. So this is my interval based on this sample. All right, so I got this interval. So this interval either cover the true mean or it does not cover the true mean. All right? But I will have quite a big confidence in this interval because the formula that I used will provide you with a probability of 95%. In other words, if you repeat this using this formula for many samples, 95% of the intervals will cover the true mean. All right? Okay, part 2. So you are given that E, the margin of error is 0.05. I want, all right, of the estimate of mu, that means x bar minus mu, off by 0.05. So it has to be absolute value. All right? It can be x bar bigger than mu or x bar less than mu. But the difference is within 0.05. So E, so this is my E, my margin of error, or the size of the error. That I accept it, and I want this to be with alpha equal to 0.05. So it turns out that N is bigger or equal to 138.3. Now because it is bigger or equal to this number, so therefore my N is 139. So that's my answer. All right? N is 139. Okay? So how about I give the answer 150? Okay, so it satisfies the inequality, but what we want is as smallest as possible that satisfies the condition. So the answer is 139. 139. And also because of this, so if you use the formula, put it this way, all right, then you got 138.3. So what is the N? Although it's not very, this is just a minor point. But then you see, if N you calculate equal to 138.3, you may do the rounding to the nearest integer, and then you take 138. All right? So that's why I want to keep this greater or equal to this expression. N is greater or equal to this expression. So that I have to find an integer greater than this number, 138.3. So the answer is 139. Not 140, not 141, because I want the smallest as possible. All right? Okay, so how about variance unknown? So in fact, this is redundant. Huh? So what I mean is that in a situation where you know the variance, then you apply the previous, the formula that we discussed just now. So if sigma is not known to you, then you apply what we are going to the formula that we're going to use. All right? So again, if the population is normal or close to normal, now but the sample size is small. All right? The sample size is small. So we use this test statistics. Okay, compared with the previous one, the previous one, we have a formula like that because sigma is known. So that is a statistics in some sense. Because, okay, what I mean is that besides the mu that we are interested to find the confidence interval for, x bar is known, sigma is known, square root n is known. So this is a statistics, all right? For you to, okay, in fact, it will be something like this. This is the statistics that I'm talking about, plus or minus. This will be the confidence interval. What I'm saying is that with sigma known, then you can use this formula because this is the statistics. But if sigma is not known, we cannot use that. So what we are going to do is to derive a confidence interval. In fact, it will be something like this. A constant is alpha over 2 or minus alpha over 2 n minus 1 s over root n. This is the one that we are going to use. So it looks as if I replace the s, the sigma, by the sample standard deviation. Because once I got a sample, I can calculate the s square, or s, in other words. But then the constant, how many standard error, then this change in order to achieve the confidence level. All right? So I consider this, the test statistics, all right? And we know that this follow a t-distribution with n minus 1 degrees of freedom. So therefore, this between these two numbers is equal to 1 minus alpha. All right? This is a random variable between, and this one is x bar minus mu s over root n. So I substitute in, rearrange it, and finally I got mu in the center. So this is my theta lower, and this is my theta upper. So this is a random variable, this is a random variable. Why is it a random variable? It is x bar, the sample mean, and the sample standard deviation. All right? So this is the random interval. So the chance of this random interval cover the mu is 1 minus alpha. Then you take a sample. Take a sample, then you look at the sample values, you calculate your x bar. You get the little x bar. All right? So the confidence interval will be x bar. Once you get the sample, you get x bar. And then you look at this s over root n. So, and the other is plus, so plus or minus. So that is your confidence interval. All right? So, so remember the key is sigma square not known. Then you replace it by the sample variance. All right? So this is my confidence interval. So when to use this formula? When sigma is not known. But in order to use this formula, you need the population follow a normal distribution. Okay? I also mentioned that is for small samples, small sample size. But strictly speaking, you can also use for big sample. That means n is big, like bigger than 30. You can still use this one. But remember, you need the underlying distribution to be normal in order this works. All right? Or the underlying distribution, the population, follow a normal distribution or at least very close to normal distribution in order to use this one. All right? So I need to, the underlying, the population has to be normal. Or close to normal, in order to use this. All right? So the difference compared with this previous formula, all right? This is the previous, when sigma is known, and the data follow normal distribution. So you use the sigma, which is known, and you use the normal, because under that, the x bar follow a normal distribution. Here, x bar minus mu over s over root n follow a t distribution. So this comes from t distribution. In fact, if you check, the interval obtained here usually is larger than the interval obtained when sigma is known. All right? Why? Because we have to take into consideration this is a random variable and this is a random variable. That means there are a lot of uncertainty. So in order to compensate it, you need a bigger interval to achieve the same level of confidence. While in the previous case, sigma is known, so there's no variation about the variance. We don't need to estimate, so we have eliminated one source of uncertainty. The uncertainty comes from X bar, or the variation comes from the X bar. So it's less varied. So the interval here, the width of the interval, compared with the width of this interval, they're different. The first one with sigma known, this one should be shorter. This one should be bigger. All right. And it's mainly due to the difference between these two numbers. All right. Okay. But for big samples, n bigger than 30, then this formula above can be replaced. All right. So we replace the t alpha for 2 n minus 1, this by a standard normal quantity, because a t distribution of degrees of freedom bigger than 30 is look like a standard normal distribution. So we don't mind to replace it by a value taken from a normal distribution. So what I'm saying is that this may be a t distribution with 3 degrees of freedom, and this may be a t distribution with 130 degrees of freedom. And this already look like a standard normal distribution. All right, so we'll replace it. So you have to understand why we replace it by a standard normal, by Z, because when the sample size is big, the t distribution with n minus 1 degrees of freedoms look like this. Where n is big, then this is similar to a standard normal. A standard normal. All right, these two are similar. So that's why I replace it by a standard normal Z alpha for 2 for big sample. All right? So here are some examples. So we don't know sigma, so we estimate everything from the sample data. So I construct the interval. I still have to assume that the data are from a normal or approximate normal distribution. All right? So here is the results. So we construct the interval is between 9.74 and 10.26. All right? Because we're only 6, so I cannot replace this by Z.025, which is supposed to be 1.96. So you can see that 1.96 and 2.447 is quite a big difference. All right, here's another example. So about the credit card. So we have a sample size of 50 credit card accounts, and the mean is this one, and S squared is 400. And we are asked these questions. What is the populations that we are interested in? Which population parameter does the chain wish to estimate? Now, it's very important. You cannot just apply the formula. You have to understand what you are trying to do. In this case, the departmental store, okay, interested in estimating the average amount of the credit card customers spent on, all right, their first visit, all right, their first visit, all right. So in other words, we are looking at all the customers with its credit card, and when they first use the credit card, how much they spend, all right. So the population here is this departmental store's credit cards customers, or the customers have is this departmental store's credit card. Okay, so this is individuals, and this individual that we're considering this population are those people, not you and me, but those people with the credit card issued by this departmental store. All right. Oh, it's hard to tell. Huh? It's credit card. This is my interpretation is means that it's the departmental store's credit card. All right, those customers that with this departmental store credit card, or at least some link to this departmental store, and the first time they use it, how much they spend. and we're interested in the average amount. So the population referred to is the population of all its credit card customers. All right. So those who use credit card, okay, forget about whether it's from the departmental store or from any credit card. So first they use it. All right. And the population characteristics that we're interested. So all the customers, what we're interested, we're not interested in the height or the weight or the CAP. We're interested in how much they spend. And also have to specify. It's not, it is the first time that they use the credit card, how much they spend. So maybe the first time they trial, they spend $5. Subsequent, they may spend $5,000. But we're only interested in the first. Everyone consider their first time that they used. All right, so since N is large, we have about 50 customers, so I can use the Z value instead of T. All right, so I take out and I use this formula. So I replace it by Z 0.05 instead of instead of T. All right, and notice that it's 90%, not 95%. So I calculate it. So the average amount, that means all the customers, the average, we estimate by 57.9 to 67.2. Yeah. Do we assume that the data is from normal distribution? In fact, we don't make that assumptions. We just apply the central limit theorem, then we still use the Z here. That means we have, okay, if x1 up to xn is normal distributed, then we are supposed to use this as my confidence interval, alpha over 2, n minus 1, and s over root n. If the sample size is big, I replace this by z alpha over 2. All right, but even if we don't have this part, we still use this formula to some sense, or in fact, the correct one should be something like this. But unfortunately, we don't know this one. So we have to replace it by S. All right? So what I'm saying is that we arrive at the same formula. If your sample size is big, apply the central limit theorem, it's supposed to be x bar plus or minus z alpha over 2, sigma over root n. But since we don't know sigma, so we estimate it by S. All right? So your sample size big, so we accept that you replace this by S, we still achieve similar confidence level. All right? But of course, if you assume that or you know that the data are from normal, all right, like this spending, first time spending, some spend a lot, some spend less, but most of them are around the mean, then it looks like a normal distribution. All right, then confidence interval for difference of two means. And this is more complicated now. So first of all, we are interested in the difference. We try to estimate this one. So naturally, you look at x1 bar minus x2 bar. This is a point estimate of this quantity. Estimate mu1 by x1 bar, estimate mu2 by x2 bar. So you want the difference between the mu1 and mu2. I give you the difference between x1 bar and x2 bar. So for mean, so the interval will be like this. Plus or minus k standard deviation, k times k multiple, k times the standard error of x1 bar and x2 bar. This, all right, is a multiple of the variation, the square root of the variation of x1 bar and x2 bar. All right? So we look at it. This is the point estimator for mu1 minus mu2. what is the point estimator for this one? So natural choice is this one. What is the point estimator for this one? The ratio. So naturally we will do this lah. Of course, the next question is hard to answer. How does this quantity behave? What is the distribution of this quantity? So we need to answer this one. In fact, in the previous chapter, we already answered this question. But we did not answer this. All right? Okay. So now we have the scenario. So when both variants are known, all right, then or the sample size is big, then we know that this follow a normal distribution with this as mean and this as the variance. Right? Variance of x1 bar minus x2 bar is equal to variance of x1 bar plus variance of x2 bar minus 2 times covariance of x1 bar and x2 bar. But this x1 bar from a sample from the first population. X2 bar is the mean of the sample from the second population. They are independent samples. So therefore, these two, all right, are independent. So they are equal to 0. So it's sigma 1 square over n1 plus sigma 2 square over n2. All right? So we repeat what we just discussed. This is a standard normal. So rearrange it. So this is the formula. Rearrange it so that mu1 minus mu2 is in the center of these two inequalities. All right, so this is the lower bound, lower limit, this is the upper limit. And you can see the difference is one is minus, the other is plus. All right, this is my constant. This part is the standard error of x1 bar minus x2 bar. The square root of the variance of x1 bar minus x2 bar. All right? So we have a formula for the confidence interval. And this formula can be used when sigma 1, sigma 2 are known. Not only that, the underlying distribution is normal. Even if they're not normal, still okay if your sample size is big, because we can apply the central limit theorem. All right? So we can use this formula, provided that the underlying distribution is normal or close to normal. If not, the sample size must be big. But in order to use this formula, sigma 1 square and sigma 2 square are known, are given. All right? So in this example 1, we have two types of engines, all right, A and B. So we have 50 experiments for engine A, 75 experiments for engine type B. And then we look at the usage of gas. So in terms of mileage, so the average, that means X bar for A, and with NA equal to 36, and this one is, NA equal to 50 experiments, and the average is 36. While XB, the average, all right, is 42. And the sample size is 75. All right. Now, look at 42 and 36. You look at these two numbers. Maybe to you, there's a big difference between these two numbers. All right. But that's not good enough. You must do calculation in order to find out whether the mu1 is different from mu2. So we want to construct a 96% confidence for mu B minus mu A. All right. And assume that sigma A equal to 6 and sigma B equal to 8. All right? So they're given. So we substitute all this and calculate. All right? Because we want a 96%, so therefore each side is 2%, so it's 2.05. And substitute in, and you've got this. So the difference between the average mileage of engine B minus engine A is between 3.4 and 8.5. What does that mean? It means that we are quite confident. We are quite confident that mu B has a higher value than mu A. How much? It's somewhere between 3.5 and 8.6. What does that mean? It means that we are quite confident that mu A does not equal to mu B. Why? Because this interval does not cover 0. Does not cover 0. All right? 0 is not covered by this interval. All right? We are quite confident this interval will cover the true answer, and this interval does not cover 0. So that means we believe that mu A and mu B minus mu A equal to 0. This is questionable. I don't believe that because my confidence does not cover 0. All right? So what happens if we have if the variance is unknown? So it's more complicated now. All right? If the variance is not known, so what to do? So so sigma 1 square and sigma 2 square are known, but the sample size is big. So in that case, I estimate sigma 1 square by S1 square. This to estimate sigma square. This estimate this one. All right? So then I use the formula. All right? So I use this one. So this basically is use the central limit theorem. All right? So that's why it is this, all right, minus, we are using this, minus mu1 minus mu2 divided by square root sigma 1 square n1 square plus sigma 2 square over n2 square. This is the standard error of this one. So this, by central limit theorem, all right, it follows approximately standard normal distribution. So what we make a minor adjustment is to replace this unknown sigma by the sample variances. All right, so we still use the formula, except that we replace sigma 1 square and sigma 2 square by S1 square and S2 square respectively. All right. So here is an example. So you can work it out yourself. Just remember, because the sample size is big, so therefore I use this in place of the sigma 1 and sigma 2. All right, so I still use Z alpha over 2, but this one, instead of sigma, I use S1 square, S2 square. All right? Remember, NA is big and NB is big. This is how we say it big. Huh? In fact, it's not that big. It's only 50 for each one. All right? Okay? So we simplified it. So the difference between mu A and mu B is minus 11 to minus 6. By the way, when I say difference, it can be mu A minus mu B or mu B minus mu A. Usually it doesn't matter. If it's no hint which one minus which, you just take either one. Either mu A minus mu B or mu B minus mu A. But if the question, or you are asked to specifically find a confidence for this minus that, or mu A minus mu B, then you have to work that out. All right? If there are no specification which minus which, you just look at the difference. So it doesn't matter whether mu A minus mu B or mu B minus mu A. The only difference is the sign that you may change. All right? If you construct the interval, let's say C, D, is the interval for mu A minus mu B. Then mu B minus mu A should be D minus D and minus C. All right? It just swap it, and then it becomes change the negative sign. All right? So this also tells you that it does not cover 0. The interval does not cover 0. So in other words, mu A and mu B, mu A minus mu B, all right, we believe that it does not equal to 0. All right? Okay, I think I have to stop here. We'll come to a more complicated equal variances. So what to do with equal variances. All right? Okay, so we'll continue tomorrow. We still have a few lectures. All right, so it will not end this Friday as the announcement. You read the announcement? You don't care about the announcement. The announcement is for group 2, not for us. All right. So my announcement will be in group 1. All right. So those announced to the all the students in these modules may not apply to this group. Like the lecture will not end this Friday. We still have to meet. I'm just telling you, for those webcasts, make no difference. All right? So please come. After this week, we still have lecture, we still have to meet.